Start that. So the last thing we went over is Theorem 3.29 right there, last time. So what we proved is that if we have some function from an interval to the real numbers, and it's strictly monotone, what does strictly monotone mean?
It's only increasing or decreasing.
Right. It's either always increasing or it's always decreasing.
Well, isn't that just monotone?
No, monotone is increasing or staying the same.
Oh, yeah.
Remember that's the difference. Rather than less than or equal to or greater than or equal to, it's just less than or greater than. So if we have some strictly monotone function on an interval, then, and if it's also, just that. So it's strictly increasing and it's on some interval, then its inverse is also continuous.
We went over that, right?
Yeah, this was the last theorem that we did. And maybe I wanted to retouch on the inverse function for a second. So the inverse function, so if we have some function from some domain to the real numbers given by f of x equals y, just two dummy variables, where f is 1 to 1, then we know that it makes sense to talk about the inverse of f. Remember, it doesn't make sense to talk about the inverse of a function if the function is not 1 to 1. Right?
Because the inverse is not going to be.
Because then the inverse isn't a function, it's just a relation. So, if we've got some function that is 1 to 1, then we have these two properties that we get to use. We have the fact that it's like the function undoes itself. You plug in y to f inverse,
Which gives you x.
which gives you an x, and then f of x gives you a y. Same thing over here. F of x gives you a y, f inverse of y gives you back an x. Right? So, just recap on common thinking that you use when you're dealing with inverse functions is little patterns like this. Undo the function or redo the function. Okay. So now we can finally, so we talked about that. So now we can finally start defining exponents that aren't just natural numbers. Right now we know how to define something like x to the n where n is a natural number, and that's the only case that we have defined so far. X to the n where n is a natural number is just x n times. If we don't right now have a definition of x to the 5/3, what the heck does that mean?
Right.
You do x 5/3 times?
I saw that in our homework. That was in our homework in 3.1.
Yeah, so like we've already talked about, what does this instructor do? This author likes to do? He likes to introduce you to problems to make you think about it before he formally introduces it. And my big example that I brought up 100 times is we proved polynomial functions are continuous long before we knew what continuous meant. So that's what we're going to do next. We're going to make sense of x to some rational number. Make sense? All right. So let's start out with the easier ones. So if we have f on non-negative numbers, not positive, non-negative, because we have 0, right?
Yeah.
So if we have f on non-negative numbers given by x to the n, why are we restricting the domain like this?
Negative to an n.
When we take the inverse, we don't want duplicate values. We want the inverse to be 1 to 1. So let's think about f of x equals x squared for a second. What does this look like when you graph it? It looks like this.
That's not
What would the inverse of that look like? That would look like this. That's not a function. So if we restrict the domain and we make this function 1 to 1, then its inverse is now a function.
I see it.
So that's why we're restricting the domain like that, if that felt kind of arbitrary. So when you restrict the domain, you make this function a 1 to 1 function. Does that make sense?
Yeah.
You cut out those duplicate values that you would get if n were an even number. So given f, we restrict it to non-negative numbers by f of x equals x to the n, the one that we have defined, we know what this one means. Then f inverse is also going to be from this interval let's make sense of that for a second. How do I know that? How do I know that this function right here, the image of this function is that? Because remember, this is from the image back to the reals. So let's make sense of this part at first. How do I know that f inverse is from 0 to infinity? How do I know if there's no negative numbers here?
Because of xn, right?
This can't ever give me a negative number, right?
Yeah.
But how do I know that this gives me every positive number and that gives me 0? Well, we know it gives me 0 because 0 to the anything is 0. Okay. How do I know that this gives me any positive number?
The real number is dense.
How do I know that for any number you pick and for any natural number you pick, I can always find an x such that when I raise it to that natural number, I get your number?
I don't know.
How do we know that?
Seems obvious, but it's a theorem problem.
Can I get really big numbers here?
Yes.
Can I get 0 here?
Yeah.
Yes.
Can I get anything in between?
Yes.
How do you know?
Because real numbers is dense.
No. It's a property of a function, not the property of a set. Just because the real numbers are dense doesn't tell me anything about this function.
Well, squaring it is only making it twice as big. Or tripling it.
But how am I guaranteed I get every one? For example, when I square the
You
natural
can always
numbers,
make a number smaller though. You can always make a number smaller. That's why I'm saying that. Like,
This strictly monotone.
what are like the two biggest theorems we've gone over in this chapter so far?
Continuous?
No, that's a definition, not a theorem.
well, there's
Extreme value theorem and
What's the extreme value theorem?
there's always a maximum.
Yeah, if it's on some closed domain, then there's always a maximum in. Okay. What's the other big one?
Intermediate value theorem.
What's the intermediate value theorem? That on some closed interval, if you get point A and you get point B, you get every value in between as well.
oh yeah.
That's what the intermediate value theorem gives us.
It's not continuous though. Oh yeah, it's polynomial.
You just avoided a marker before I even threw it. Good job. Yeah, that is for sure continuous. There's no question about that. So that's continuous. And by the intermediate value theorem,
We know it all.
I can get any real number here. Right? I can always get a number, pick any real number you want. I can always get a number bigger than that. That's really easy, just plug in that number.
Right.
Or plug in a number bigger than that number. And we'll get an even bigger number out, right? And I can get 0. Therefore, I can get any positive number you can think of to come out of this. Right? I didn't want to plug that in as a side proof, but maybe I should have. Does that make sense?
Yeah.
Okay, so we don't need to prove it? Okay, so the domain of the inverse function is 0 to infinity. This part makes sense?
Yeah.
But why is it to the reals? Why is it to 0 to infinity?
Because that's what we're dealing with over there.
Because all we need is the image just has to be a subset of that. We can always just put the real numbers on the right hand side. We don't need to try and limit this, right?
Oh, I see. Yeah.
Don't try limiting this when you're dealing with functions. Don't make it hard on yourself. We
You're
could
saying-
have.
You're saying none
It's
of
just
it
hardware.
will be negative.
I'm saying we want to, even though we know that the inverse function is never going to spit out a negative number, don't make it hard on yourself. Don't put that here because then you have to keep track of that when you're like doing your proofs and stuff. You got to make sure you keep that in mind. Don't make it harder on yourself.
Okay.
That's all I was going to say there. Okay, so if we restrict this function to this domain and it looks like this, then its inverse is continuous. Okay? How do we know its inverse is continuous? By this theorem right here. It's from an interval to the real numbers.
And it's strictly monotone.
Oh, sorry. I was playing the wrong thing. This is strictly monotone, and it's on an interval to the real numbers. You see this?
Uh-huh.
Yeah.
That's why it's continuous. Good?
Yeah.
So the inverse function is continuous. And that's another reason that you can think about the intuition why we restricted the domain, because now this is strictly increasing.
Right.
If we didn't, then we'd have the part where we go down where it's decreasing, then increasing, which then is not a strictly monotone function. Okay. And so it has these two properties, which are the same thing as these two properties, if you look closely at it. The inverse of the function gives you back x. That's this. The inverse of f of x gives you back x. The inverse of f of x gives you back x. And then the inverse of y, and then take f of it, gives you back y. Maybe say it this way. F of f inverse of y is y. F of f inverse of y gives you back y.
Okay. So the top one, why is...
We know what f of x is explicitly.
Oh, it's f of x right there.
F of x explicitly is this.
Right.
We don't know what f inverse of x is yet. We don't have another way of writing that. Well, now we're going to invent another way of writing that. We're going to write it like this. So now we're making a definition. What do we mean by f inverse of y? Or sorry, what do we mean by y of 1 to the n? We mean f inverse of y. We mean whatever goes right there. Whatever you plug in right here, such that when you raise it to the end, you get back y. Okay? So that's our definition of y to the 1 over n. It's the inverse function of f of x to the n. Or f of x equals x to the n. Y to the 1 over n is the inverse function of x to the n. It's the function that undoes that. It's our definition. Does that make sense? So it's the thing that you plug in right there. Or could have plugged in right there, right?
Yes.
Because x to the n is y.
Yeah, because that x cancels.
In other words, what I'm saying is, now I can, with this definition, I could rewrite these two things like this. And I didn't change anything. Now we have a definition for what this thing means. This means this. That's what we're saying.
Right.
Nothing weird, right? Am I stressing this too much? Let's do an example real quick, maybe. What's 4 to the 1/2?
I get that. 4 to the 1/2 is going to be 4. Is going to be 2 to the...
Okay, we're
Okay,
getting
probably
trouble with that.
no, it's 4 to the...
It's 2!
Well, yes, I understood that, but yeah, I was trying to show it that way. Oh, yeah, 2, that way.
It's just 2.
Right,
Why? Because 2 squared is 4.
right. Okay, yes.
Right? Just apply the square there, apply the square there. What do you get? You get 4 is equal to 4. Another way to see it. We need to do another one?
Okay.
I'm just confused on how you brought that.
Yeah, that's
F
really...
inverse of y. And
Did I write something wrong?
not wrong, it's just really confusing.
You're saying right here? F inverse of y. What's y? X to the n.
Why are you using f of x?
X to the n is y.
Oh, sorry, I didn't specify that again here.
Oh,
I see why I'm confusing you guys. I kind of mixed this and this together in my head. Sorry. F of x equals x to the n, or y equals x to the n. Or f of x equals y as well. So I'm using y to designate the thing that x to the n mapped to.
Okay. So the
A
inverse...
particular x goes to a particular y. So the inverse of the output
to the n.
plugged through the function gives you back the output.
Oh, plug through the function, x of n.
Yeah, notice that this is a function.
Yeah.
Let me rewrite, that's why I started out saying, this right here is the exact same thing as this.
Yeah.
And this right here is the exact same thing as this.
Okay.
Oh. I can perfectly see that.
Yeah.
Going from here to here, we plugged in what f of x was. We got rid of the f's. There's no longer that f and there's no longer that f. And now that we can have another way of writing the inverse, going from here to here, we got rid of the f inverses with a 1 over n. Good? Alright, let's try another one. Let's do 8 to the 2/3. we're going to use some properties that we haven't used yet real quick. Such as, this is the same thing as 8 to the 2 to the 1/3. There's one way that we can think about it. Or we could have thought about the Bent array, which is 8 to the 1/3 to the 2. Four?
Yeah.
Good. It's equal to 4. What cubed is 8? 2. Or in other words, what's the third root of 8? 2. And you'll probably see where we're going with this, but the way that we have it, x to the 1/2 is the same thing as the square root of x, right?
No.
And x to the 1/3 is the same thing as the cubed root of x, etc.
Yeah, man.
So, okay. So you get comfortable with these things in the denominator and how they're an inverse
Yeah.
of what goes in the numerator. One more way that I should be really intuitive. What do I have if I have x to the n over n?
X.
I just have x. I have x to the 1. I have x, right? So if to the n does one thing, to the 1 over n undoes it. It gives you back what you started with. Another way to view it. Okay. So, the inverse function. So now we have a definition of what we mean by y to the 1 over n. Right? We mean the inverse of x to the n. Whatever that is. Or the inverse of y, where y is equal to x to the n. We wrote that. F of x.
Look, I know. Like that one too. Same thing.
Okay. Another thing, now we've defined it for when we have x to the n and x to 1 over n. Now we need to define it for negative numbers. Let's define it for integers now. So if I have x to n, that's the same thing as 1 over x to the negative n. Or in other words, I don't know why the author wrote it this way. It's actually an ugly way to write it.
Yeah.
I like writing it this way. X to the n is equal to 1 over, x to the negative n is equal to 1 over x to the n. Definition. It's not something you prove, it's what we're defining. So now, what's 2 to the negative 3? 1 over 8. Easy peasy.
Yeah.
What's 2 to the negative 2?
4.
No, that's 1 over 4.
Oh my.
Oh, 4. Yep, look at that. Algebra still works out.
Hey, you got me.
You don't know how to divide 1 into fourths? How many fourths go into 1? Whoa! The third grade way about thinking about division. Okay, here's what you're going to do as a homework problem. You're going to prove that x to the n plus n is equal to the product, and you're going to prove that x to the n is equal to x to the product.
How? By using
For any
theorem.
integers. You're going to start by proving it for natural numbers. Do induction for natural numbers, and then you handle the 4 cases.
And we're going to use these theorems. There's one theorem actually.
These definitions more than the theorems. I don't know that you need
Oh my goodness.
a theorem.
Well, we don't even know what it means for two exponents to be added to each other.
You know what addition means.
No, we don't.
You know what addition means.
Okay, but how do
You know what x2, an integer, means. What's the sum of 2 integers? An integer. So that's just x to an integer. And it turns out x to that integer is the same thing as x to that integer times x to that integer.
How in the world are we supposed to prove that?
Good luck.
Alright, I will find
You're
you.
supposed to try.
And I will kill you.
And if you can't, Google it.
I do.
If you still can't, then we can go over it.
Just kidding, Google will have that one.
Of course it will. Huh?
I don't even know where to start.
Prove it for, okay, prove it for natural numbers and
But
then,
how do I prove x times x to the n times x to the n is x to the n plus n? How do I prove that? How do I show it?
so base case, we're proving that x to the n plus 1 is equal to x to the n times x, right?
How do they know that? How do they know that? Where did we prove that?
This has been our definition for x to a natural number already.
Oh,
We already know, if you don't mind the pi notation, x to the n is equal to the product up to n, starting at k equals 1 of x.
Right.
It's x times x times x times x times x times x times x, n times. That's what x to the n is.
We've done that. Remember how we were doing our summation proofs?
So this is almost the exact definition.
Okay, I'll use it, but
So are we going to use proof by?
I mean, if you want to write it really explicitly, what does that equal? By definition, that equals the product to m plus 1, starting at k equals 1 of x, which we can rewrite that as the product of n, k equals 1 of x times x, which we can then write as x to the n times x. There's our base case, really explicitly. And then assume it's true for m equal to k, so that implies it's true for m equal to k plus 1. I think if you just tried it, it wouldn't be as
We
hard
will
as
be using proof by.
induction.
proof by induction. It is an inductive proof. Yes. The hard part is when you go from naturals to integers, because then you got to worry about the negative cases. Anyways, continuing. Alright, so now we've got our definition for x to a natural number, x to 1 over a natural number, x to a negative number, right? Now, let's do x to a rational number, period. So for some positive number x and r equal to m over n, where m and n are integers and n is greater than 0, or in other words, r is a rational number and we choose to write it so that the denominator is positive.
Right.
What's a rational number?
Anything that can be divided.
It's just a fraction.
yeah.
Okay, if it's a negative fraction, put the negative in the numerator, not the denominator. That's what we're saying, right?
Okay.
So we're saying, let r be a fraction where the thing that's in the denominator isn't negative. So those are two integers, but the thing in the denominator is not negative. So r is just a rational number. So we're just proving, we're just defining x to some rational number.
Okay.
And our definition for that is just this. X to n, which is an integer, which we know, then that to the 1 over a natural number, which we know.
Right.
That's our definition for that. Anything weird there?
Each piece.
Okay. And then our last proof for the section, we need to prove that these things are continuous. Because this is now not necessarily a polynomial, right?
Right, because it could be fraction.
Mhm.
It has to be natural numbers.
Right. It could
Right.
be rational.
So now let's prove that this is continuous. So first off, we always restrict to the domain, right? The key that we're going to use here, by the way, is that function composition is continuous.
Okay.
So if I have
Function.
f is continuous and I have g is continuous,
F of G.
then f composed with g is continuous.
We proved that.
Yeah, we did. As long as the image of this thing is in the domain of this thing. Right? In other words, if this maps to 3, 3 better be in the domain of this thing.
Okay.
Oops. I did that backwards, sorry. Because we're doing f first. That's composed.
That seems like a pretty heavy condition.
That the image of this thing is in the domain of this thing. You can call that heavy condition if you want. But as long as the image of this thing is in the domain of this thing and these two things are continuous, this is continuous. Okay? So I'm going to write this thing as a composition of two continuous functions. Okay? And then show that the image of one's in the domain of the other. And obviously, what are my two continuous functions? They're those two functions. So I say, let's see, I already used f, so we'll use g and h. Let g from 0 to infinity to r by g of x equals x to the n. And let h from 0 to infinity to r by h of x equals 1 over n.
X is 1 over n.
Oh, thank you. Equals x to the 1 over n. And f is equal to h composed with g is continuous. Right? Could have done a little bit more work explaining why the image of one's in the domain of the other. But remember what we already know. The image of any of these functions is that same interval.
Right.
So the image and the domain are the same for this function and for the inverse as well. That make sense? So I already know that, where is it? I already know that the image of this thing is the domain of this thing. They're the same. So this is continuous, and the image of this is in the domain of this. Therefore, their composition is continuous, which is exactly what f is. So since f is a composition of two continuous functions, such that the image of one lands in the domain of the other, f is continuous.
So now we know that x of r, where r is rational, is continuous.
Yeah, correct. And then obviously, the sums of those and the products of those are also going to be continuous.
Which have to prove on homework.
Well, I doubt you'd have to because that's really trivial,
I think.
right?
Right.
Because you could view sum adding two functions together as a composition.
Right.
And addition is going to be continuous, and multiplication is going to be continuous. So as long as you're not dividing by 0 or anything where descriptive domain is fine.
So is it implied that h is continuous?
We already know that h is continuous. That's what this is. What is h? It's the inverse of x to the n.
Well, how do we know m is a natural number?
M is an integer. N is a natural number.
Oh.
Where n is greater than 0.
But x to the m is not continuous.
X to the m is continuous.
Where do we see that? Because our polynomial has to be a natural number.
Because rational functions are continuous.
Well, we just proved that.
Well, x to the m, you have two cases. M's a natural number, or it's not. Three cases. M is 0, m is positive, or m is negative.
Right.
If m is positive, this is continuous. Right? We already know that. Because it's a polynomial at that point.
Polynomials have to be natural numbers.
Right. If m is positive, we already know m is an integer.
Right.
If m is positive, this is a polynomial, it's continuous.
It's 0.
If m is 0, this is 1, it's continuous. If m is negative, so now this is negative n, it's equal to 1 over x to the n, which is a rational function, which is continuous.
A rational function.
Rational is a quotient of polynomials. The numerator and the denominator are polynomial.
Oh, true.
As long as this is never 0. I didn't specify that. Should have specified that.
True. Polynomial divided by polynomial. It's going to be a continuous.
Right, we already proved that. And we proved it directly because we know that the quotient of the limit is the limit of the quotients. That's what we use to do that. Anyways, so yeah, we know that x to an integer is continuous. As long as you don't divide by 0. Right?
Right.
So we good with this?
Will you explain that over there again?
I don't know what that is. You're saying everything?
You said h is continuous because of.
Okay, that's what we were saying right here. We're saying if f of x is x to the n, and it looks like this, then its inverse, which we now define as, what is f inverse? We now have a way of writing that. F inverse of x is equal to x to the 1 over n. 1 over n. What we're proving right here is if this is, not if,
Yeah.
given f like this, its inverse is continuous.
Okay.
So 1 over n is continuous is what we're proving right here.
Okay.
Because we just said it's continuous, and then we defined that inverse, that continuous thing to be 1 over n.
Yeah.
Right? Any other questions?
Okay. Chapter 7.
Yeah, so moving on to chapter 7, limits. Before we move on to chapter 7, I need to make sure you understand something very clearly. Every single time I've done something like this in this class, it was shorthand for the limit as n goes to infinity of x of n. Okay? So every time I wrote this, this is what we were thinking about.
Right.
Now, in chapter 7, we're going to talk about taking a limit, but it's not necessarily going to be as n goes to infinity.
Okay.
It's going to be, well, here's what we're going to see. You're going to see the limit as x goes to some number. Well, I'll introduce a new notation as it comes up, but just understand, so far when I've written this, it implied this,
Yeah.
right? Okay. So let's just start with that side conversation. We'll no longer be able to use that shorthand because now when we take the limit, from here on out, every time we take a limit, it's not always going to be taking the limit as n goes to infinity. We could be taking limits different ways now. That's what I'm trying to get at, just so I don't confuse you with that. Okay. So let's talk about the limit point of a set. So remember, now this is a property of a set. We're not talking about taking the limit of a function. We're talking about a limit point of a set. A limit point of a set is if there exists a sequence in the set that converges to that point, then that point is a limit point of a set. Okay? So let's do a quick example. Let's say I've got 1, 2 here. What are the limit points of this set? 2 is a limit point of this set. How is 2 a limit point of that set? I can find a sequence in this set that converges to 2. What is that sequence? That sequence is going to be 1 plus, what do we want?
1 plus 1 over
1 over n, almost doesn't work. 1 over n plus 1, is that what you said? So start at a half. 1 plus n. No, that converges to 1. Oops. So 1's also a limit point, right?
That works.
This converges to 1.
Converges, no, that converges to.
This converges to 2.
Yes. No?
Yeah.
Plus, 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 plus.
Do we need to write this? Yeah, let's look at the sequence. What's the first term in the sequence? 1 plus a half, right?
Yeah.
And I'll just keep writing that way. What's the next term?
1 plus.
1 plus 2 thirds.
Oh, I thought
1
we
plus
did
3/4.
summations for some reason.
Okay, you see how this converges to 2?
Yeah.
And then when I had the other way, when we didn't have and in there we just had 1, I said this converges to 1, right? What does that give us? 1 plus 1 half, 1 plus a third, etc. You get it. So the point is, 1 and 2 are limit points of this set, even though they're not contained in the set.
Oh, are those two y values or two?
We're not talking about functions.
Yeah, I know, but those are two. Those aren't the inputs and outputs. Those are just the outputs.
We're not talking about inputs and outputs.
Is it a series
We're not talking about a series.
or a sequence?
A sequence. We're saying if there's a sequence that exists in here, so for any point x, given x, x naught. Let's say it this way. If there exists xn in D such that the limit as n goes to infinity, I'll try to write that now, of xn is given x naught, given x naught, if there exists xn in D such that the limit of xn equals x naught, then x naught is a limit point of D.
Right, then we close.
Remember it, we're defining it right now.
We already defined it.
We might have talked about something like this, but
We defined what it means to be a limit, as long as it converges.
we talked about a limit, but now we're talking about a limit point of a set. A limit point of a set. It's a property on the set. So let's look at the set 0, 1 again. What are all the limit points of that?
1.
We set 0 and 1. What else is there?
Anything in it?
Anything in between. So all the limit points of this turn out to be the closed interval 0, 1. Any of these points are limit points of this.
That's not an interval, though.
Yeah, this is an interval, this is an interval. This is a closed interval, this is an open interval.
Okay. Yes.
Both those are intervals. Does that make sense?
Yeah.
It's not just the endpoints. For example, 1 half. Can I find a sequence in here that converges to 1 half?
That's
Yeah, 1 half, 1 half, 1 half, 1 half, 1 half, 1 half, 1 half. That converges to 1 half. And there's infinitely many others that we can come up with that converge to 1 half, right? Okay. So that's what we mean by a limit point. The important thing to note is that while every point in this interval is a limit point, there's also points outside the interval that are limit points.
like 1 and 0.
Like 1 and 0, exactly. We good with the idea of a limit point?
Yeah.
Okay. Another example that they do. What are all the limit points of A, B? Where B is a number bigger than A?
A and B and everything.
The closed interval A, B, like that, right?
Yeah.
Okay.
So you're telling me that I can find a sequence that's only in here that converges to B?
Yes.
What is it?
A over or
I start with an A plus, so I'll help you with that.
A plus A over A plus 1.
Or do a B minus is another way you can do it. We could do B minus, let's see, the distance between them, and then divide the distance to something smaller than the full distance. Make that minus. Okay. There's something that converges to B.
Yeah.
And if we want to converge to A, switch this out for an A and make that a plus.
Can you just
There's
say
something
B?
that converges to
Can you
A.
just say B minus 1 over N? We don't know what's.
Yeah, just make sure we don't go outside the interval so we get its distance. Make sure the distance is less than the full distance. So we're still outside the interval. And keep multiplying by n to make the interval get smaller and smaller and smaller. Good? Okay. notation, when I say D slash and then some set, this means all the points in there that aren't this point. It means this set minus that set. Okay? In discrete math, we just used a minus sign. Same thing. This set minus all the points here. So now let me write down the book's exact definition of a limit point now that I think we're comfortable with what we're talking about. Now once again, I can't specify this enough. A limit point is a property of a set. I'm not talking about a function. Because I don't want you to get confused by what we were just doing. So, definition. For some set of real numbers D, then x naught in R, some real number x naught, is a limit point of D provided that there exists xn in D minus x naught, so not including x naught. Oh, I wasn't specifying that before, but I should have. Such that the limit as n goes to infinity of xn equals x naught. Mark that.
Black. We wrote black.
I think that black one is the same black one I was using last time, which was close to dead. Oh, it's not bad. For a while. Okay. Does that definition make sense?
No.
No? Okay. So, D is just some subset of real numbers.
Okay.
And we're trying to say whether or not x naught, which is just some real number, is a limit point of D. Okay? So if there exists some sequence
Okay.
that doesn't include x naught in D, if there is some sequence in D that doesn't use a point x naught, such that its limit is equal to x naught, then x naught is a limit point.
Yes.
Are you saying that x naught can't be in xn?
Correct.
Okay.
Just like your
X naught never shows up in xn.
So in the interval 0 to 1, like 1/2 can't be a limit.
Right. No, 1/2 can, but we couldn't use the sequence 1/2, 1/2, 1/2, 1/2. We'd have to use the sequence 1/2 plus 1 over 2n, something like that.
Right.
Okay.
Oh, sorry, like that. In the interval 1 to 2. Is that what you said?
Yeah.
So there's a sequence in the interval 1 to 2. No, you said 1/2.
0 to 1.
Oh,
0 to 1.
0.
Okay. 0 to 1. Does that keep us in there? When we plug in 1, we get 1. We can't go to 1, so I'll put a 3 down here so we start from 3rd. Okay, there we go. So there's a sequence that's always in the interval 0 to 1 that converges to 1/2, but never uses a point 1/2. And since the limit of that is equal to 1/2, then 1/2 is a limit point of the interval 0 to 1.
Okay.
That make sense?
Yeah.
So I'll bet you we prove that there are infinite.
So it doesn't mean that it's not in the interval. It just means that this, like your xn, doesn't start with 1/2. Doesn't have 1/2 in it, right?
So I want to know if x naught is a limit point of D. If I can find a sequence in D that never uses x naught, but converges to x naught, then x naught is a limit point of D.
Okay.
Does that make sense?
Yeah, but Yes, but it doesn't mean that it's not in an interval.
No, every point in an interval is going to be a limit point of that interval.
Okay.
So not necessarily every point in D is going to be a limit point of D, but if you have an interval, then for sure.
Okay.
That make sense? Alright, let's think about this. So this isn't a sequence, this is a set. Let's look at the set 1, 2, 3. What are its limit points?
1, 2, 3.
Yeah. What are the limit points of that?
2 minus 1. Oh, wait, 1, wait.
Wouldn't it be
All 3 of
three?
them. Oh, yes.
Yeah, all three of them?
There are no limit points.
No, they are.
Find a sequence that converges to this that doesn't use this, that only uses these.
3 minus 2.
Oh.
3 minus 2 is 1. That's a number. You just use 1.
Oh, yeah.
You can't,
Right.
right?
Mm-hmm.
But when I gave you something like 0 to 1, we knew what all the limit points of that were. It was a closed interval, 0 to 1. Good? Just trying to help you wrap your head around these limit points.
Mike, can you go talk to Ben after work? Levi's on break, so he has time to take 35 minutes.
Sure. Let's go on break and then we'll finish after, I guess.
Sorry.
Oh, now you can't shut me. Let's go.
Oh.
guys are good with all those?
Yeah.
The juniors are fascinating to me.
Wow.
Yeah,
Who's more fascinating, juniors or sophomores?
seniors clearly.
That's the question.
Well, I know the sophomores more than I know the juniors, so. Which is kind of sad, but. Hey, are we watching movies tonight?
Yeah, we need to, don't we?
Yeah, we need to watch Harvey, because that's when James is.
What are we going to be there on Wednesday? Are we doing auditions on Wednesday?
No. We are just delaying and delaying. I honestly think we should do it the week of. Yes, that's what we are doing.
What?
The week of sophomore trip.
I think so.
Fourth
We have our
weekend?
first performance on Tuesday
It's
and
the
then
best
on Friday.
option. I think is.
I get to Brotherham 2 days ago. Dress rehearsal Monday. We could do
You want to do Tuesday, Wednesday, Thursday,
Touch-up
Friday?
practice
You want
Sunday.
4 practices.
huh?
What, 4 practices? Or
I don't
4
think it's going to be
days?
as big as we think.
Actually, we
Besides
can't.
the stage.
Yeah, it's gonna be hard to set up the whole stage from Sunday to dress rehearsal on Monday.
No, because we can set up the stage.
Actually, Aaron did that whole stage yesterday.
We can set up our stage right after Easter program. Because then you have third weekend, which you just put it in that back half of the room, which nobody puts chairs
Oh.
in.
I say, yes. That's why I'm saying this. Do it 2 weeks after Easter. Well,
That
give a
means-
full week between the Easter concert. That gives you a ton of time to practice on stage, and then just that Saturday night, take down the stage real quick, set up for church, and then that Sunday night, we should all as a class reset up the stage.
You wouldn't even have to take down the stage.
You would. Oh, if we do it in the back, you wouldn't. I thought we decided we were gonna do it.
Oh, we are gonna do that?
Seems like the better choice. Because Synergy just got new lights, which I don't know if we'll be able to hang.
That would not be a problem.
What it is. And another problem I have with it is usually in the back room, they only ever did stages that were tall. Like, they built their stages high, so you didn't see so much of the back wall. And we could still hang curtains and stuff, but. That's
Yeah,
just
I
a
guess it
whole
would be
dynamic
nice to
I haven't
have
thought
the
about.
back office.
Alright, let's continue. So next we were talking about, so far we were talking about limit points on a set. Okay? Now we're going to switch gears a little bit, and now we're going to talk about the limit of a function now as it goes to a point. So we're going to talk about, where did I have it? We're going to talk about the limit of f of x as x approaches a particular number.
Well, haven't we been doing limit of series or what?
So far, we've been talking about convergent series, right? The limit as n goes to infinity. Yeah, not series sequences. We were taking the limit as n goes to infinity, then the nth term in the sequence got closer and closer to a particular number. So now, another way to view it is we're going to start talking about the limit as the sequences numbers get closer and closer to a particular number. The terms in the sequence get closer to a number. Instead of saying the index goes to infinity, we're saying the term gets closer to a number. That's going to be the difference in how we talk about limits now. Does that make sense? Okay. So, let's make clear exactly what we mean. Did we already go over this part?
No.
Oh, sorry, let's do this. Did we do this?
Yes.
Okay, so let's start with what? Sorry. Go back to talking about limit points. A limit point of a set, and then we'll talk about the function. So limit points of a set. Let's do another example. We've already talked about like open intervals, 0 to 1, stuff like that. Let's look at this one. Every real number is a limit point of Q, the rationals. So I'm saying for any real number you pick, I can always find a sequence of rationals that don't include that number that converge to that number.
Oh, that's about it.
Does that make sense? That's what we're going to prove. You with me on what we're trying to prove?
Yeah.
Okay. So let x not be some real number. Could be rational, could be irrational, we don't know. But it's just some real number. So now our job is to find a sequence in Q that converges to this number, but it can't use this number. Right? So we know that Q is dense. What does it mean to be dense? It meant for any open interval you pick, I can always find a rational number in that open interval. That's what dense was, right? So since Q is dense, then for any open interval you pick, x naught to x naught plus 1 over n, I can always find a Qn in there. So let's read it now. Since Q is dense, then for all natural numbers, there exists a rational number such that that rational number is in x naught to x naught plus 1 over n.
What's the definition of this?
So Q sub 1 is a thing in x naught to x naught plus 1. Q sub 2 is a thing in x naught to x naught plus 1 over half. Or 1 over 2. Etc. So we're making our sequence Q sub n this way. Right? So now Q sub n, it doesn't include x naught, right?
Why?
Because
It's always in here. This is an open interval. So it never includes x naught and it converges to x naught. So Q sub n is a sequence in the rationals minus that thing. And the limit as n goes to infinity of Q sub n equals x naught.
Why do we know that?
Because it's always in here.
Yeah, but that's
It's always greater than this and it's always less than this.
that's not the definition of convergence.
Right. We can spell it out with the comparison lemma.
If we could, then yes.
You understand how you'd use a comparison lemma, right? This Qn is always less than this thing.
Right.
And it's always greater than this thing. And this converges to this.
Yeah.
Okay, that makes sense? So is it obvious to everyone that the limit of Q sub n is now x naught?
Yeah.
Okay. So that was limit points, but remember that's just talking about a set. Now we want to start talking about the limit of a function as it approaches a point. Let's do intuition first of why we're doing this. Ignore the function I have right here, but just look at this function right here, this line. Now notice something. If I ask you what's the value of the function at 0, what is it?
1.
1. What's the value of the function at 1?
nothing.
Nothing. It's not defined at 1. But you see how this whole thing is approaching a particular value and this whole thing is approaching a particular value? Limits enable us to handle this picture. So even though the function at 1 isn't 2, the limit of the function at 1 is 2.
Oh.
So the limit of the function as it approaches a point, most of the time it's just the value of the function. But now, here's a point where the function doesn't have a value, where we can still talk about the limit of the function at that point. Okay? So we're going to be interested in the limit of functions at a point. What does the value of the function get closer and closer to as our inputs get closer and closer to the number that lines up with it. Right? So in other words, we are going to be interested in what's the limit of this thing as x approaches 1. What's the limit of f of x as x approaches 1? And we know in this case it's 2 from the picture, right? But if I were to say what's the limit as x approaches 0 of f of x equal to?
It doesn't have.
No, it's just 1. It's just a value of the function. That's real easy.
Okay.
So this happens all the time with people who study calculus. They think limit points have to be points that aren't defined. No, most of your limit points are obvious. This is the tricky point. This is the hard point.
Okay.
Does that make sense?
I don't know how it's hard. Why is it?
It's harder because you have to think, oh, it doesn't have a value there. Most of the times, the limit of the function is just the value of the function. The limit as x approaches 0, oh, that's 1. For the limit as x approaches -1, oh, that's 0. Okay? So don't think that the limit has to always be talking about weird cases where the function wasn't defined. Don't let that happen.
Okay.
And I would bet you guys even got confused by that when you did calculus.
Probably.
It's such a common thing. So, limits enable us to talk about these points, but they don't only talk about these points. We can talk about the limit of this function at any point we want. Good? So that's what we mean intuitively. I want to talk about the limit as the function approaches a point. That's what we need to come up with the definition for. So that this notation right here makes sense. Okay? That's the notation we're trying to make sense of. So given some function from some domain to R, and some real number x naught, then we say that the limit of f of x as x approaches x naught is L. We say that this is the case provided that there is some sequence in G that doesn't include that converges to x naught, such that the limit of the sequence is L.
Okay.
Okay? So in other words, if I can find some sequence in D that doesn't use x naught that converges to x naught, such that the limit of that sequence is L, then I can say the limit as x approaches x naught of f of x is L.
That seems like the same thing from up there. Up there, top.
Up here.
Yeah.
Almost.
I don't see where it's not.
In other, this was a limit point of a set. Now we're talking about the limit of a function as x approaches some value.
Okay, so as x approaches value, right at that.
In other words, if I know that the limit of x goes to x naught of f of x equals L, if I know this, then what do I know? Then I know that there was some sequence in the domain that doesn't include x naught, such that the limit, sorry, we usually have it written like this. No, we don't. How do we normally write this one? Like that? Sorry. I don't know if I'm throwing you off with my notation. Hopefully that's not throwing you off in any way. But what are we saying? We're saying anytime you see this, what does it mean? If you see this, then you know that there is some sequence xn in the domain that converges to x naught, whatever that number is, such that the limit of the function of x naught equals L.
Okay.
Okay?
Now what does that mean?
Huh?
Now what does that mean?
It's the definition.
It's our definition for what this notation means.
Okay.
What do we mean by this? We mean that there's some sequence in the domain that, a better way to say it is, we know that x naught is a limit point of the domain,
Right.
and that the limit of the sequence is that L.
Limit of the function is that.
Oh yeah, the limit of the function of the sequence is that L. Good catch. That makes sense? And so you can go back and forth between taking the limit as x goes to x naught of f of x, or taking the limit as n goes to infinity of f of x n. You can go back and forth between thinking about these ways, whatever floats your boat. Just make sure you do your limit correctly for however you're doing it. Are you doing the limit as x goes to x naught, or are you doing the limit as n goes to infinity, where you're dealing with xn, and xn converges to x naught? Notice they're kind of saying the same thing, right? x keeps getting closer to x naught, or xn keeps getting closer to x naught. You plug in bigger n's, xn gets closer to x naught, or x's get closer to x naught. You see that? Okay. So let's do some examples. Oh, side note, which I think we've already fleshed out here. But if x naught is in D, then f is continuous at x naught if and only if the limit as x approaches x naught of f of x equals f of x naught. That's almost identical to our definition
If x
of
is
continuous. What did continuous mean? The limit of the function of the sequence equal
The limit of
the function of the limit of the sequence.
Oh.
Right?
That's if x naught.
The limit as n goes to infinity of f of xn equals f of x naught. Or the limit as x goes to x naught of f of x equals f of x
It's
naught.
not that bottom one right there. Limit as x goes to 0 of f of x is.
Yeah, so since I know that the limit as x goes to 0 of f of x is 1, since I could find a number that makes this true, I'm guaranteed that the function is continuous at 0. Because 0 is in the domain and its limit exists. Is this function continuous at 1?
No,
Why?
because 1 is in our domain.
1's not in the domain.
Or 1's.
This function is not defined at 1. 1 is not in the domain of this function.
Wait, how do we tell the difference?
Huh?
Okay, yeah, never mind.
You know just by my drawing that 1's not.
If we had the actual function.
Well, here's the function, but I didn't specify its domain.
Well, 1 minus 1 is 0, so what's undefined?
Right, it's undefined at point 1, so we know 1 can't be the domain if it's a function. But so, if a point is in the domain and the limit of the point exists, then it's continuous at that point.
Right.
And that might have been the definition that you guys used for continuous, I don't know.
That actually sounds a lot more familiar than our epsilon delta.
Okay. So continuing. So that was just a sign out that, hey, we're looking at the definition of continuous again. Right? Okay, so now let's do examples where we actually find the limits of some things. What's the limit as x approaches 2 of this function? Well, that's really easy. It's just the value of the function. Just plug in 2.
Okay.
Right? Because the limit as x goes to x naught of f of x is just going to be f of x naught.
Right. How do we know it's continuous?
When x naught's in the domain. This is continuous.
Oh,
Remember, that's to the 1/2, that's to the 1/2.
right.
Well, it's continuous at 2 if it's defined at 2, and if f of x naught was
So
a
because you defined it at 2 with 3 over 2, then it's continuous.
Well, we know that this is continuous if 2 is in the domain,
Yeah, I want to get out of the habit.
and if plugging in 2 gives you a number,
Okay, if 2's in the domain and if plugging in 2.
and plugging in 2 gives you a number.
Okay. And the number is saying therefore it exists, right?
How do you know if 2 is in the domain? If
Right, we
it
didn't
is-
specify it here whether or not 2 is in the domain, so maybe this function is or isn't continuous at 2. If 2 is in the domain, then it's continuous at 2. We can define the domain to be whatever we want, right?
Yeah.
But most of the time we assume that the domain is all possible real numbers that don't break the function. So the domain of this would be all real numbers except for whatever I plug into this, it gives me 4. Right? Anyways, most of the time this is what taking the limit looks like. The limit as x approaches 2 of this is just 3/2. It's just whatever you get when you plug in 2. Right? Okay, let's do another example. Let's do the limit as x approaches 1 of x squared minus 1 over x minus 1.
So it's going to be 2, but I don't know.
Now notice we can't just plug in 1. Uh-oh. And I graphed the scene for us over here so that you can see what's going on. Uh-oh. We can't just plug in 1. It doesn't work. So now what? That's the question. So now what? How do we handle this thing? Because remember, when we're taking the limit, we never actually plug in 1 to this thing. Right?
We say,
We're plugging in numbers really, really close to 1. We're saying not if you plug in 1 what you get.
right.
We're saying what do you get if you plug in numbers really, really close to 1. In other words, if I go to the left just a teeny tiny bit, what number do I get?
Right.
Or if I go to the right just a teeny tiny bit, what number do I get?
So what, you plug in n over n plus 1?
No, I guess it's
You could do kind of what you're thinking. You're saying 1 plus 1 over n, right?
Yeah.
Plug that in and take the limit of that as n goes to infinity. Yes, you could do that.
Okay.
That's one way to do it. Might get messy if you do it that way, but you could do it that way. Because this is true for any sequence that gets closer and closer to 1. Any sequence that converges to 1. That doesn't use 1.
Oh, so could we even,
Or you could look at this. That's a difference of squares.
no, I can't look at that and just say that.
Okay. Oh, that's a difference of squares. I don't know how to make it more explicit that that's a difference of squares than to write 2 squares there with a negative sign between them.
What is difference of square?
Means it's easy to factor.
Oh, okay.
X minus 1, x plus 1.
Right.
Over x minus 1.
Holy cow.
Whoa!
Yeah, that's yes.
I don't understand.
All of
So what?
We're never plugging in 1 here, right? So we're never dividing by 0. So we can do the algebra that we want to because we're never dividing by 0. So I have an x minus 1 down here and an x minus 1 up here. Those cancel out.
What's the way to think about this now? Now if we plug in a number really, really small to 1,
So the way to think about it is the limit as x goes to 1 of this function is the same as the limit goes to 1 of this function.
and now we can...
Because as long as x doesn't equal 1, this is equal to this, right?
holy cow. Oh, it's bad memories.
So that's why this thing's so easy to graph. Graphing this thing is just going to be the graph of x plus 1, but there's one bad point.
So that, I don't know where I'm confused with.
You get what we're trying to do overall? Should we try it your way? Let's see what happens when we do it your way. Might get a little bit messy, but
You could erase this stuff right here.
that's okay. Let's just give ourselves plenty of space because I don't know how bad the output's going to take off. So, really working ourselves, we can take the limit as n goes to infinity of, what was our function? X squared remember, we're using x of n equals 1 plus 1 over n, right? Something that converges to 1. So we've got that squared minus 1 all over 1, not 1, x minus 1 minus 1. I got it, right? Is that what it is? So now let's just do all the algebra. That's equal to the limit as n goes to infinity of squaring this thing out. What do we get? We're going to get 1 plus 2 over n plus 1 over n squared. Did I do that right?
Yeah.
And then in the denominator, 1 minus 1 just leaves me with a 1 over n.
Yeah.
Okay with that? Okay. Which is equal to the limit. Let me simplify the numerator. Should have done this before. We have a 1 and a minus 1 there, right?
Yeah.
So now I have,
N over 2 plus.
and I'm going to write this kind of different. So we have the 2 over n, right? plus the 1 over n squared. And then divided by 1 over n is the same thing as times n, right? Which is equal to 2 plus 1 over n. Sorry, the limit of that.
That is cool. Actually worked out pretty well.
So same thing.
As n goes to infinity, that goes to 0.
Yeah, we had xn equal to this. Notice we created some sequence such that the limit of xn equaled x naught. It's that. Right? So instead of doing the limit as x goes to x naught, we can do the limit as xn goes to infinity. As long as xn is never equal to x naught, which it's not. We never use 1 in here. Same thing. So, yeah, you're really stuck. If you can't figure out how to do the algebra, you can think to yourself, all right, what's a sequence that converges to 1? That doesn't use 1. Plug that in, and you get the same thing.
Well, what you had was x plus 1.
X minus 1, x plus 1. Sorry, you're right. The limit as x goes to 1 of this thing is the same thing as the limit as x goes to 1 of this thing. Which is equal to the limit as x goes to 1 of this thing, which is equal to 2.
So, why is it equal to 2?
As soon as you
The limit as x goes to 1 of x plus 1,
1 plus 1.
1 plus 1 is 2. Remember, if you can just plug in the number, do it. It's only when plugging in the number doesn't work that you got to get tricky.
Okay.
So up here we could just plug it in and it worked. If it doesn't work, then you either need to come up with some sequence and do all that algebra, or see if there's some trick. All right, let's look at this one. Obviously that's a difference of
squares.
no, not squares. What's bigger than a square? A difference of cubes. Wonderful. We have x to the 1/3 cubed minus 2 cubed over x to the 1/3
Oh my goodness.
minus 2. Right?
Yeah.
I'm not going to write the limit over and over again, but
Yeah.
should write the limit over and over again. I'm just going to run out of space if I do that. So now, a difference of cubes. We can factor. So we get x to the 1/3 minus 2 times, let's see, what does that leave us with? X to the 2/3 plus 2x to the 1/3 plus 4. Did I do that right?
No. Because your first, oh yeah.
Yeah, you did.
That right.
I think I did it right. Yeah, that's right. And then those cancel out, right? And so now you just plug in 8 to this, and whatever you get is your answer. So that's 4 plus 4 plus 4. 12. 4 plus 4 plus 4 is 8. Good?
Yeah.
All right. This next theorem we're not going to bother proving, but because it follows directly from what we already have. But if I have these two functions, same domain, x naught's not in the domain. If the limit as x goes to x naught of f of x equals a, and the limit as x goes to x naught of f g of x equals b, then the sum of the limit, the limit of the sum is the sum of the limits. The product, or the limit of the product is the product of the limit, and the limit of the quotient is a quotient of the limits, as long as that thing's never b and the limit's not b. Sorry. As long as that's never 0 and b is not 0. As long as we don't break anything.
Yeah.
So the way that they prove that is they do what we did over there. They they switch this to the limit as n goes to infinity of some sequence, and then we can use our previous proof. And then you're done with this. And the same thing for, well, maybe this one's worth writing out. Group all this. Not even 11 yet? Good news.
What section are we line to work with?
1, 2, 3.
2, 3, 9.
Probably 3 first, then 2. I did 3.
You checked my 3.
You did not. I was reading like someone's proof last night, and there was a comment on the proof online. Oh, I got this problem when I was a sophomore in high school. And I got it again when I was taking my exams in college. So real analysis is being teach somewhere when I was in high school.
Yeah, I mean, there was a kid that I was going to school with who was 17 who graduated with me.
What the heck?
He graduated with his bachelor's in mathematics with me.
17.
Yeah, 17 years old. He was a fun kid to do problem with. He always had such unique proofs for doing things. Like his way of proving things was not the standard way of proving things that other people would use. He always had his own little flair, his own way of thinking about it. Often using other material for the class, like a bunch of his discrete math proofs were using linear algebra concepts. But he's a fun kid to go to school with.
Have you seen Spider-Man, the new Spider-Man?
I don't think so.
Does he remind you of like Peter Parker? Does that be cool if he?
It's very clear that I see someone who's supposed to be a genius on TV that does a good job portraying himself as a genius.
I just imagine that 17-year-old as Peter Parker.
Peter Parker is a baller.
Alright. Suppose that x naught is a limit point of D such that the limit as x approaches x naught of f of x is equal to y naught. And that y naught is a limit point of u such that the limit as y goes to y naught of g of y is equal to L. And that f of d, except for x naught, is a subset of u minus y naught.
What do you know?
17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17.
limit of f of x is y naught, right? The limit as x goes to x naught of f of x is y naught.
Yeah.
And the limit as y goes to y naught of g of y is L. Then the limit of this is L. Kind of not formally proving it, but using what we already know about composition of limits from before. We would write this as the limit as x goes to x naught of gf of x is going to be the limit f of x as x goes to x naught is going to be y naught, right?
Right.
So the limit as y goes to y naught of g of y is equal to L.
Here's where I'm confused. F of x is equal to y naught, right? So you have g of.
No, the limit as x approaches x naught of f of x is y naught.
Yeah. So.
Look, we're viewing this is some sequence that converges to this. So if I do y equals f of x, then saying y goes to y naught is the same thing as saying f of x goes to y naught. Right?
In what you just said again.
So replace this f of x with a y, you're good with that,
Yeah.
right? So now this is our variable. Well, instead of looking at it as x goes to x naught, we're now looking at it as y goes to y naught.
Oh.
Because f of x going to f of x naught, I shouldn't say it that way because f of x naught might not be defined. But,
Okay.
is it clicking?
Yeah, it
Yeah.
feels like inverses all over again.
Yeah.
Even though.
Not inverses.
No, it's not inverses.
Composition.
But we're using f of x to find a y.
Maybe it'd be worth just flat out writing the proof.
With the g.
Let's just write it. It's not even that big. And I don't want any confusion in your head. So, if it's at all being confusing, let's just do it. Alright. One. Let x n in d minus x naught such that the limit of x n is equal to x naught.
No, it's not sushi. Because it'll take too long.
Are you eating sushi tonight and then what tomorrow?
Instead of sushi tomorrow, go to Dairy Queen tomorrow. Because we can't get sushi tomorrow because we won't have enough time. So it starts at 7:30. It's a Dairy Queen tomorrow.
You want to go to
And then that makes it way cheaper.
Probably fast.
Oh, you want to go on Thursday?
Sushi. Sushi's charged.
What?
You're telling me you'd rather sushi over hamburger?
I'm telling you, I'd rather steak. I bought cheap.
Oh, you can make that at home, dude. Might as well just do steak night. That would actually be fun.
That'd be a lot of cooking.
That?
It would not. Wouldn't be that much.
That would be fun. We should buy James and lamb.
You just not want to go to sushi.
Yeah, sushi's
It's
lame.
so expensive. That's the only problem I have.
Oh, that's the biggest problem. It's like, why would we go travel an hour to eat at a super fancy restaurant for $25?
Yeah. When I could
When
go
I could eat food
to
I'd rather
Subway
eat.
and get a really good sandwich for almost $1.
Alright, there's a whole proof.
They're doing like hamburger.
You just use one sequence to define another sequence.
This is a proof?
Yeah.
I thought this was a definition.
No, not a definition. We're saying, look,
It's like
if f is some function that converges to y naught, and g is some function that
Converges to L.
such that as y goes to y naught, g of y goes to L, then, oh, I didn't write the then. Sorry. Then the limit as y goes to y naught of, no, not y goes to y naught, as x goes to x naught of g composed with f of x is equal to L.
Not xn
In everything indeed not including x naught,
right.
such that it converges to x naught.
Right. Observe that limit of f, right? That y n equals
xy.
F of xy, sorry, where is he in that?
xn.
Oh,
Oh, x and.
yeah, sorry.
It's like.
That's an x. And we're just making the sequence yn that converges to y naught.
Right. Okay. We G to G, dude.
So, composition works just as you'd expect it to. Okay. Yeah, we can do homework now if you want.
Okay.
Can I get my homework back in?
Yeah. I hope you can. All this kind of stuff is your guys'. I didn't grade that. I forgot you gave me that.
So you didn't go through and correct it?
Oh, sorry. Completely forgot about literature test. I don't know if I already gave these back or not, but here's your test. That's from forever ago.
What?
Way back. The test that you gave me.
Did you correct it?
Uh,
Wait, no.